I made, I'm not going to make slides. I didn't make slides. I rather made some sort of, I don't know how to call it, like a blog post, a collection of links. And I kind of guide you through this text that then you can read later, because as you, maybe I should start press record. I don't have the permission to record, Eva. So if you can make both of my accounts.
Yeah, sorry,
co-host.
I will do that.
There's two Enrico in the participant. The one that is talking is not going to record. One will record. So if you can make also the other one co-host, yes. Okay, now we start. So I thought that than making slides, which sometimes are not very useful if the presenter is not around, I thought to structure things into a blog post, which is some sort of like a reflection full of links and references, because as you can imagine, how to make your code reusable, how can I say, spans so many topics of computational science and open science and digital preservation and many other things that, you know, basically one should have a workshop that lasts for many days if you are really serious about making your code reusable. So here I'm gonna kind of guide you through this series of links. I could actually share the link in the chat with you so that you can also browse it. It's still work in progress, so we're still revising it with other people, but you can already read it and download it, save it, and in the end it will be stored in our usual spots under aalto.fi and scicomp.aalto.fi. All right, but let's get started. There's 20 people here. So the question for today is like how to make your code reusable. And the definition of reusable is, you know, able to be used again or more than once. And there's a nice, you know, example, which is, how can I say, even related to the environment, you know, that we want to have reusable shopping bags, for example, so that we can use plastic over and over. So my first statement is that code reusability is a requirement for reproducible science. Of course, not all science is using code, and not all science, you know, is quantitative and needs to do processing, but there's lots of science that is quantitative science and that is based software that is used to process data. So if you want to work with the reproducible science, you most likely need to also work with reproducible code. As I write here, science that cannot be verified, reproduced, replicate is not science. It is luck that, you know, you were able by some fragile combination of things to make something and even publish it. But, you know, maybe we shouldn't call that science. And the same thing is about the code. So here there's a funny cartoon from the monkeyyuser.com where they show, you know, an implementation in a company or whatever. You can think that this is your research group, and, you know, the researcher is saying this is the code base, and the reviewers are of course amazed, you know, wow, it's such an amazing piece of software, you can do so many things with it. But then, you know, the ugly background of the hardware and dependencies, as it says here, it's all hidden and it's all obscure, and the knowledge about these things might be limited to only few people. So you can already see that this is a scenario that is very typical in the industry as well as in academia. Another funny comic, if you are a Python user, let's do actually a quick round using the Zoom buttons. So if you click on participant with your Zoom, you should see some buttons that are yes, no. So if you are a Python user, can you press yes? And if you're not a Python user, can you press no? It doesn't mean that you have, you know, that you are devoted to Python, but it might be that sometimes, you know, once a month you use Python. So I can count that more than 50% of the people in this room are Python users. So most likely you came across these issues with the so-called Python environment. And this is a funny comic from XKCD, but this is something that I have experienced almost weekly, and our users, because I also help the people, the users of Triton, they also experience very often. So fragile code that cannot be rerun is not going to help the advance your science. I guess we can all agree on this. Now, so I've been talking about reproducible science, and we have some nice upcoming lectures on reproducible science. And here I'm citing in this link the Turing Way, which is an amazing book, collaborative book written by many people around the planet. And in one section of that book is the guide for reproducible research. And then there they define 4 concepts in reproducible research. And I will guide you through these 4 concepts because these are very important, even though these are not strictly related to software. So the idea is that if you have the same analysis, which in our case would mean the same software, but also, the same data collection protocol, the same, version of operating system. So as much as you can keep the same in the processing, protocol, analysis side, methods, and also the same data. So the data that you have collected or that you have downloaded or whatever data. So you want that your science is reproducible so that, in 1 month or in 6 months or in 6 years, you can reuse the same code and the same data and, get out the same results. And this might seem like a trivial exercise because it's like, of course, the code is the same and the data is the same. Why wouldn't it produce the same results? But this is not trivial at all. And you might experience this yourself if you submitted the paper and after 6 months or 12 months, you get replies from the reviewers. And then you have to go back to what you did 6 months ago or 12 months ago. And you might feel lost. You might not be sure which script was run first and which was run after. So, even this supposedly trivial stage is not trivial at all. Then things start to get more interesting when other people might be collecting similar data, or maybe your colleagues collect basically a different data set that could still be processed with the same methods that you have used. So now it gets interesting because now the data is different. And if the results that you're going to have are, how can I say, somewhat compatible with the original results, then you can start calling your science replicable. So, other people can verify what you did, even with new data. So it was not that you were just lucky with that single data set, but other people are able to, replicate your science. And then, of course, there's other interesting things about the science that we do, because someone else might use the same data that you have, but use a different method, a different pipeline, a different tool, a different programming language. And if they're also able to get the same results, then you could say, that those results were not just about the luck of your tools or your setup or your operating system, but they are so-called robust results, so that with other methods, with other pipelines, you can still get the same kind of output. And this is where kind of, Newton lives, or Galileo Galilei, your science becomes generalizable when other people collecting other data using other tools, but somewhat similar to the experiment you did, are still able to get the same results. So like, if you want to measure the speed, the gravity, the g, the acceleration of gravity, then this is quite a generalizable finding. But I'm not gonna, of course, the focus is more narrow. It's about the code. So I thought that it was useful to kind of reuse these concepts from reproducible science and adapt them to code. So basically, although not all the 4 concepts can be, straightly adapted, I came up with this kind of 3 categories of reproducible code. or reusable code. So the first category would be reproducible code, which means that you or somebody else can basically reuse the same code and the same data and reproduce the exact same thing you did. So this is the scenario that in 6 months, when the reviewers ask you to rerun your analysis, you can, you're not lost, and you can rerun it and reuse it and even reproduce the same results. And then eventually change some parameter if that's what they ask you. Then the replicable code is when maybe you want to reuse bits of your code for a new project, or someone else wants to use the bit of your codes for their own data. So now things starts to change a bit. So, it's not exactly the same data, and maybe not even exactly, but well, actually we can think that it's not exactly the same data, but it's still the same code, the same core processing that is going on. And then, and this is the maybe most difficult bit, is when your code needs to kind of leave the boundaries of the original experiment, of the original study that you did, and needs to be generalizable, meaning that other people can start building on top of it. They can extend it, reuse it, and improve it. And this is where, that's the greatest benefit for science, of course, and also for yourself as a researcher, because people can cite you and, and you get famous. So the last statement here that I write is that reusable code becomes sustainable. And you heard about the sustainability many times, I'm sure, because it greatly contributes to the community, and not just to the users, but to the whole science. So if you start from scratch, from when you start a new project, if you have in mind that your code will be reusable and will be published and will be available, you are contributed to sustainable science. All right, so this is in one view, at glance, all the kind of steps or rules, or how can I call them, things that one should need to take into account to basically reach the most simple, supposedly trivial task of being able to rerun the same code with the same data and get the same results. Then they're a little bit less trivial, to reuse the same code with different data, or whether it's you reusing it or someone else reusing it with different data. And this is when people needs to actually open your code, read it, and build on top of it, extend it, and generalize it. So I made multiple points, and now we can go through them. But if there's any questions, you can of course write on chat, raise your hand, or otherwise I can continue. I'm going to try to leave a bit of time for discussion at the end, because each of these points that I'm mentioning has many links, and that points to other reference. As I said, the whole thing here could easily be a 3-day workshop. It is actually a 3-day workshop, because we've been running these things with the Code Refinery Network. And basically for any of these points, there's a Code Refinery video already there on YouTube for you to watch and learn. But now I'm gonna also go through the motivations why you should, or maybe why you would like to consider all these points that I'm listing. So the first scenario, which is the supposedly trivial scenario of rerunning, reusing the same code with the same data to obtain the same results, it has some requirements. As I write here, you might not even need to open the code. You might not even need to read again the code, but what you need to read is kind of the manual. How did I run this code one month ago, 1 year ago? Which steps did I follow to prepare the data, prepare the software installation, and then which order of steps? So this supposedly trivial step is maybe the most difficult one, in my opinion, or the one that requires knowledge that it's usually not taught in nature science, or even in social sciences, or sometimes not even in computational sciences. But of course, it's this kind of knowledge that you come across if you start working with code, because you see other people using these tools. So the first thing, and here I mentioned the FAIR principles, if very briefly, if you don't know what is a FAIR principle, they stand for. Usually they are referred for data, but they can also be thought that they apply also for methods and for code. So F is for findable, A is for accessible, I is for interoperable, and RE is reusable. So the first thing you need to do, that you should be able to find the code. And I'm saying find in space, in the sense, find the location where this code is stored. If you can't use a car if you don't remember where you parked the car, even if it's an amazing car. But if you have no idea where it is, that's it. You are basically lost and you need to build a new car. And for sure, we often rely on our memory. So we know that in a subfolder of a subfolder of a subfolder of a project, there is the final version of the code, but that's just you. And in 18 months, maybe you don't remember anymore which one was the right folder. On top of that, you're not working alone, okay? In some cases, you are a one-man lab, a one-man researcher, but even in that case, you are working with someone else, which is your future self. So, but more often, you're gonna work with other people, whether you're part of a lab or you have a supervisor or you have some students, whatever is the case. So here, we often cite the so-called lottery scenario. You're gonna win the lottery today, and you decide tomorrow to disappear, move to a tropical island and live forever happy and stop thinking about science and code and this kind of stuff. And nobody can reach you anymore. There's no way to reach you ever again. So now it's the task of your colleagues to start going through your files, through your folders, and hopefully find which version you were working on. So the simple solution is that from the very beginning, you should store your code in a place that everyone knows where it is. There are nice repositories for code that, for example, GitHub and GitLab, even if you work with the sensitive code, there are still ways and solutions to have your project private, to make sure that you can share the code with others in a secure way. So, you know, there's no kind of excuse for not doing this. And even better, you might want to get a so-called persistent identifier. So identifier for papers, but it's the same thing here. So you want to have an identifier that maybe in 1 year or in 5 years or in 10 years, people can still find that version of your code. And zenodo.org allows, for example, to archive releases of code where they kind of get the timestamp and they are there as long as, you know, as long as we need them, basically. So here I already introduced some concepts like GitHub and GitLab. They talk about version control. And I linked here this code refinery lesson for version control. Now, the reason of version control is more clear in the second bit, because not only you should be able to find your code in space, so where is the digital, if not physical, location of your code, but you also should be able to find it in time, because the code is dynamic. What I'm writing today might be a little bit different than what I wrote last month, even though it's the same script, the same piece of code, and it might change again in 6 months. So there are tools which are called version control, where you can basically temporal snapshots of the state of the code, so that you can easily say, okay, I submitted this paper 7 months ago. Can I get that snapshot from those 7 months ago? Because I don't remember if I already fixed that bug or not. And you can basically, you know, not only find the code where it physically lives, but also find which of the many versions you were using. And of course, ideally, you would like to version your code in a sense that you have release numbers and version numbers, something that is, you know, usually done with the more larger projects. But even in your single lab, single scientist project, it doesn't hurt to attach a version number to your scripts and the date, for example, when you changed it. All right, so now we kind of took care of finding and accessing the code. And of course, now that's not enough. It might be that now we have the code, we have the exact code that we were running 6 months ago, but we're not able to rerun it because the code lives usually, or if not often, if not always, in a fragile environment. So the environment is a fragile snapshot in time, which accompanies the code. It can include the human who operated the software, all the steps that the human did to prepare the data, the hardware that was used, the operating system, the libraries from the operating system, from other packages, toolboxes, dependencies. So all these things, you might just ignore them because maybe you're lucky and your code will run again with whatever new libraries and new hardware in 1 year or in 6 years in the future, or maybe not. Or maybe your code needs to be, how can I say, preserved in a sense that you need to remember what was the environment, the hardware, the software, and all the other dependencies, like I was showing earlier in that cartoon. So Code Refiner has a nice lesson on recorded dependencies, and if there's time at the end, I can show some of the solutions that they present there, so you can learn this yourself. So of course, recording the environment, it's still like a snapshot of kind of, you know, the how can I call it, the structure, the kind of the static snapshot of the code and the environment that was there. But of course, there are dynamic steps that happen, meaning that often the code that we run is not just a single script that will be run once and will do everything. Often there are multiple scripts doing different things. One is doing the preparation of the data, one is doing some generation of results, one is doing some plotting. So the order of steps needs to be also documented. And of course, you can rely on the humans and hope that the human can document. For example, you know, you are using a graphical software interface, let's say Excel. And in Excel, you really need to document. I clicked on that column, I sorted the data with that function from Excel. I selected from row 1 to row 50. You know, all these steps that you do with the mouse, you should also write them down in a so-called README file. But as I say in the next point, if you are really working, if you want to make something really reproducible, maybe you shouldn't rely on humans. Maybe you shouldn't rely on anything that requires a human to point and click into something. Just because humans can be, you know, we're not the best in avoiding errors. And on top of that, all these interfaces, all these dynamic, you know, click and point tools, they might easily change, and there might be no way to get back to the same interface or whatever program was used 1 year ago or 10 years ago. So then if you get rid of the human element and you know that you can write a non-interactive single script that kind of runs step after step all the bits that are needed in the environment that is kind of, you know, the same environment that you had 1 year ago or 10 years ago, then you know that you have basically reached the so-called reproducible code. You can, somebody else can rerun exactly the same step on the same data with the same environment and get exactly the same number. So this introduces more advanced concepts like the concepts of containers like Docker and Singularity, which I can cover at the end if there's time. The idea of pipelines and the pipeline script, whether it's a single script with all the steps one after the other, or the so-called direct acyclic graphs where there's many dependencies, and with tools like SnakeMake, you can basically, you know, have more complicated pipelines. So this was part one. Part two is that, okay, now we are hopefully able to reproduce the code, so we can reuse the same code we made a few years ago, a few months ago with the same data and get the same results. But then sometimes we want to replicate the code. We want to reuse it in a sense that we have new data, that we have new people in the lab or new collaborators that want to reuse the same, they want to redo the same thing you did with the original data, but with a different data set or with a different set of parameters because they want to change some of the parameters you used in your model. So the first step here is, that you actually need to open the code and start fixing it to make so. In the previous part, we didn't even need to open the code. We just need to make sure that we can kind of replicate all around the code to make it to recreate the same point in time where the code was run. But here we need to start opening the code. And the first bit is that if there are hard-coded bits like the path to the data, some hard-coded numbers that make it difficult for somebody else to reuse the code, they should be separated from the actual core modules, from the functions that are processing the data or doing something. So that basically you need to make your code modular, split the bits that are related to that specific project you ran 6 months ago or 1 year ago, and make the code that can be reused into functions. There's a nice presentation here on modular code development with many interesting things. One, the most important take-home message is that you should make your module pure. Pure means that given the same input, they will produce always the same value, the same output. So this is kind of the definition of that we have in mathematics in calculus with mathematical functions. Then of course, because now other people will start inputting new data or inputting new parameter, you should start thinking of what are the options, meaning what kind of parameters, what kind of data can people input it. And you need to test for any possible, you need to test that somebody will try to input all zeros. You need to test that somebody will try to input, or I don't know, not the numbers. So you need to kind of start thinking that when people start using your code, you need to think of the scenarios so that your code can be tested. And this is another big topic in computer science, which is the so-called automated testing. Here there's a link for a code refinery lesson on automated testing. But the idea is that by building modular pieces of code that can be tested, you can immediately identify new cases that you didn't think of, because they will start breaking a test. And then maybe you know that, okay, I need to work out a new section, a function that needs to take care of this case that I did not think about. And then furthermore, if we were able now to separate within the original project the kind of hard-coded bits of the specific project with the more generic modules, functions, then it makes sense to turn the modules into a package so that actually maybe these functions and this module can start living their own life, because so then it's easy for you to reuse the same package in other project so that you don't need to track multiple copies of the same package across multiple projects. And also it's useful for the others because they can just point to the package and download it, install it, and hopefully be able to run it like you did. And here that's some nice couple of links on packaging software in general. This is a presentation. This is a more hands-on how you do software packaging in Python with pip. All right, so now we kind of took care of we were going from kind of the most time consuming, which is making the code, what's the word, reproducible so that it can create the same numbers. Then another time consuming bit, which makes the code reproducible, so replicable so that other people can start using it. And then this is maybe the most simple part, because it doesn't require, or you don't necessarily need to know about containers, Docker, Git, version control, and other things. But here it's actually on one hand the easier part, because you don't need to learn all these other tools, but the most difficult part because it requires your effort from day zero. So to make the code generalizable so that other people can use it and build on top of it, it means that people need to start opening your code and read it. We are not just talking about users that they just trust your code, will never open it, and they're just happy to run it and get some numbers. There's many examples like that. There's many Python users in the room here. You might have used NumPy. How many of you have really opened some NumPy, source code to basically check that, I don't know, whatever mathematical operation is right? I trust a lot the developers of NumPy, and I'm just a NumPy user. But if one day I want to start developing something new, maybe I need to actually open the original code and see what I can start improving, what might needs to be changed. So the first thing, if people really need to start opening your code, you need to have a license with your code, meaning that you need to tell people how, can they build on top of your code, and how can they reuse your code. If there's time at the end, we can show there's a nice example of the so-called code licensing using cakes. So, and a metaphor that you have a cake recipe, and you can decide if you want to make the recipe open source or closed source. And of course, licensing comes with your rules for citations. So if people use your code, reuse your code, build on top of your code, they can start cite whatever thing you tell them to cite. Maybe you publish the software itself, or maybe you have a paper attached, kind of, that introduced the software. So there's also benefits for you. And this is, I can say from personal experience, this is very clear. I've been sharing always the code with my papers, and then some codes have been used in completely different fields, but because they were able to find it and reuse it, then they just cite my paper, where I basically write in the license, please cite that paper if you reuse that code. And then another very difficult thing, that the only way to fix it is that you need to make sure that your code is readable by humans. Sometimes people, especially people maybe who have a computer science background, they might write obscure code, one-liners, meaning that in a single line of code, there's many statements that are executed. Maybe, I don't know, with some obscure idea, maybe in some programming languages, it might be very efficient to have in a single line, but with things like Python and MATLAB and R, it doesn't really change for the machine if you have a single line with all the code that you need to run, or if you split it in multiple lines and make it readable. So this means that the machine is able to read your code, even if you write it in an obscure way, but the human is not going to be able to read the code. And the human can be you in 6 months, or can be somebody else that would like to reuse your code. So there are many, how can I say, conventions and good ways of basically writing the code, giving meaningful names to the variables, giving meaningful names to the functions. So all these things that, the code, the more readable the code is, the easier it is to spot errors or build on top of it and make improvements. Which kind of goes with the next step, which is the so-called comments in the code. Comments are free. The machine will not take care of that, so you could have as many comments as you want. And what I recommend myself, and I try to do myself, is that before coding anything, I just write the comments. I just write the whole comments. Now, in multiple sections. Now do this. After this section, there will be something else. And then, so that once all the comments are written, I know which bits of code need to go where, and I can start writing the code between the comments. So the idea is that you should imagine that somebody could just read your code by skipping all the code and just reading the comments. So then they know, okay, which part does what, but just reading the comments. And then when they find the part that they want to improve or reuse or whatever, then reading the code and changing it. And the last one, which you must have heard, is of course documentation. Some people say that the code is self-documenting because it's so beautifully written, or because there's amazing comments. But in my opinion, this is not true. A good documentation is not just about me being able to read your comments in your code or bits of your code written well, but it's also being able to kind of, get help out of your code. This link I'm gonna now share because this is an excellent example of how the code should be documented. This is from the NumPy project. This is just one function in the NumPy project. And here in this function, immediately at the top, I have the so-called signature of the function. So what parameters can I type? What can I get out? The meaning of each of the parameters and what am I getting out. And then, and this is often missing in the comments or in the code, there are examples. So how can I actually run and test? I could then now copy this bit of code here and make sure that I get the same plot that they get here. So that, and then start changing for my project. So documentation is, there are also here nice way to build documentation, and there's a link to another code refinery lesson for documentation. So basically now it's 10:40. I was able to cover everything, and here at the bottom, so you can get all these things that I mentioned as a code refinery lesson. I'm going to open the link. So there are introduction to version control with Git, collaborating, sharing over Git, automated testing, modular code development, and many other things that I mentioned already. And what it's interesting, and you find it also here at the end of this post, is that you also can see everything as a YouTube. So if you click here, this is now, I'm going to press stop, but this is a full playlist of the last, or one of the last code refinery workshop in May, divided in multiple parts. Usually when we do these workshops live, they last for 3 days. Online, they last for 6 days, so that we just do 3 hours per day. And here you can type along with the speaker and basically get better idea of all these topics that I mentioned. Be open with questions. If you want me to go deeper on any of the bits, I was mentioning, for example, this is interesting, the scripting pipelines and Docker containers. But of course, so whatever you in this room want to get out of this, I'm happy to expand a little bit more. Here's the summary of everything, if you want to see it again. So any questions? Or was I so clear that there's no questions? Practice, there's lots of work to do from my side, from your side, from anyone's side. Good code, reusable code doesn't come for free.